This is one of the strangest facts I know about simple programs. This tiny 8-bit rule was once trusted enough to sit inside Mathematica's random number generator. So before we even ask why it looks random, we already have a sharper question. What kind of toy rule earns that kind of trust? The object itself is almost embarrassingly small. You start with a row of black and white cells, and to compute the next row, each cell only looks at three things: its left neighbor, itself, and its right neighbor. 3 input bits means 8 possible local patterns. So a rule like this is really just an 8-bit lookup table. For each pattern, output either black or white. That gives you 256 possible rules in total. Rule 30 is just one of them. Now start from the simplest initial condition possible, one black cell, and then just apply the same local update again and again. Nothing hidden is happening here. No injected randomness, no changing parameters, no clever schedule. The same one-line rule keeps hitting the row above. And that is where the object starts to feel wrong in an interesting way. From a completely rigid rule, you get this pattern that keeps looking scrambled. Once the whole triangle looks messy, the most revealing thing to do is not to stare at all of it. It is to ask whether one thin slice already behaves like a random source. So take the center column, the cells directly under the original seed, and read them as a string of zeros and ones. In a sample of 10,000 bits, the balance comes out almost perfectly 50-50. And this is not just a cute observation after the fact. For 2 decades, Mathematica used this exact column as a source of pseudo-random bits. But a 50-50 split alone is cheap. Plenty of non-random sequences can fake that. A better sanity check is compression. Truly patternless data is hard to compress, and ordinary coin flips are the baseline. So I took 10,000 bits from the center column, matched them against 10,000 fair coin flips, and ran bzip2 on both. In this sample, the Rule 30 column compresses no better than the coin flips. That does not prove randomness. It does tell us that the obvious large-scale shortcuts are not showing up. By this point, you almost want to say the center column is random and move on. But the actual mathematical situation is harsher than that. There is a $30,000 prize attached to proving some of the natural things you would now want to say about that center column. Does it eventually repeat? Does it really settle to equal densities of zeros and ones? Is there any systematic test that separates it from genuine randomness? The evidence is strong. The proof is still missing. That gap is the real subject of the video now. If you zoom way out, you might expect some larger order to take over, some hidden regularity, some visual clue that the chaos was only local. But thousands of generations later, the texture still refuses to settle into something obvious. The question does not go away when you give it more room. It just becomes harder to ignore. The rule is tiny, and even the program that generates row 1000 is tiny. But as far as we know, there is still no shortcut that jumps straight to row 1000 without effectively doing the computation. The simple description does not buy you a simple prediction. That is why Rule 30 lingers in your head, not because it is complicated, but because it is so small and still seems to withhold any cheaper explanation of itself. That is computational irreducibility in its most unsettling form.